So our next speaker is Kamalika Bhattacharjee, and the paper name is First Degree Cellular Automata as Pseudo-random Number Generators. Kamalika is from Department of Computer Science and Engineering, National Institute of Technology, Trichy. So over to you, Kamalika.
Thank you, Shubhanadi. Can you see my screen?
Yes.
So yesterday I talked about this emulating machine twister based on cellular automata. Today I'm going to talk about first degree cellular automata, which is also going to be used as pseudo-random number generator. So as both of the work was based on pseudo-random number generators, I have taken some slides from the previous day's presentation to make it complete. So for the sake of completeness only, I'm going to show it. If someone is is joining only today, then for them it might be useful. So pseudo-random number generator is basically the numbers which appears random but can be reproducible on demand. This reproducibility comes from the background algorithm, which is called the pseudo-random number generator. And the period of a PRNG is the number of steps after which the seed or the initial state of the PRNG comes back. There are several classes of PRNGs, like linear congruential generators, LCDs, linear feedback shift register based or LFSs, and cellular automata based. Here we'll be concentrating over the cellular automata based generator. And there are several properties like uniformity, independence, large period, reproducibility, efficiency, coverage. These things are supposed to be satisfied by a good pseudo-random number generator. This table also have shown in the last day's presentation. Here you can observe that the status of the CA-based PRNGs in accordance with the existing other PRNGs of like LFSR-based or LCG-based. Here, if you observe here, if you increase the number of states from 2 to 10, that is the decimal CA, they are performing very well like the competitors at the best PRNGs, which is not belonging to the class of CAs, that is the SFMT 19937 or variant of machine twister. So therefore, decimal CAs are good contender to be good source of randomness. But the problem is, if we increase the number of states, the neighborhood combination will also increase. For example, if we take 3 neighborhood 10 state CA, just like the decimal C I was showing, the neighborhood combinations becomes 1000. Therefore, although we can get some suitable PRNGs by changing number of states, but there will be this difficulty of presenting the rule in pen and paper, and that is a representation of the rule, how we can represent it simply or how we can simplify it. For example, in the decimal CA, in that paper there was 2 algorithms. The simplified algorithm also, or the simplified form of the representation also required one algorithm to find the actual rule or the actual function that is going to be the local rule. Another problem that arises is exhaustive searching of the CA rule space to find which CAs are good. That is practically impossible, because if we increase the number of states, then accordingly number of possible rules is also increased. So this is very difficult to deal with. Therefore, in this work, our target is to develop a greedy solution to find some good as well as easy to describe CAs. Now, our target is to find easy to describe CAs and good CAs. To make it good, we have to ensure that some randomness properties are going to be satisfied by those CAs. Here we take one-dimensional 3 neighborhood 10 state CAs under periodic boundary condition. However, the schemes work for any distant neighborhood CAs. So as I have taken 3 neighborhood combination, the rule is S cubed to S, where S is the set of states, and the domain of R is X, Y, Z, the left, self, and right neighbors. Now, as Najimandi was telling, this combination X, Y, Z is called rule mean term or RMT in our work, and it is represented by its decimal equivalent. There are 2 other terms associated with the RMTs. One is equivalent RMT, another is sibling RMT. Equivalent RMTs are the RMTs which satisfy this equation, and sibling RMTs are of this, which if we divide by D, it will give the same value. There are some other well-known terms associated with the CS like fixed point attractor, self-replicating RMT. Self-replicating RMT here is for which the R of X, Y, Z is Y. Balanced rule, that means the same number of next state values for each of the states in the rule, and a de Bruygerian graph, which is a well-known mathematical tool to represent any overlapping sequence, and it is well known in the field of CA. Now, let me first talk about the desirable properties. First is balancedness, that is no affinity towards any state. If we take the rule as balanced, obviously we can ensure that there will be no biasness towards any state in the rule. So this target is satisfied. Next is non-linearity. In yesterday's presentation, we were discussing about the usefulness of non-linearity. Here we have the choice of taking the CA rule itself as non-linear, and we have done that. And then large cycle length, that is the period length is to be very large, but the problem is here we are taking periodic boundary condition, and in periodic boundary condition we can't get maximum length. So our target is we want to take those CAs for which there is less partitioning of the configuration space, making the cycle length as larger, and it should grow, the average cycle length should grow exponentially if we keep on increasing the cell length n. And then the last property is flow of information, which is very important to ensure that the CA is a good contender for randomness. It is the dependency of each cell on its neighbors. This ensures that if we change the value of any of its neighboring cells, then that information will be to traverse to the next cell in the neighboring, whatever is the neighboring cell, and it will be propagated through the time steps. How we can measure that? There are 2 ways. One is left directional flow of information, where we can consider the sibling RMT set, which sibling RMT set means these sets which have this, if we take sibling RMT set for here, it is, I have considered D equals to 3. These 2 values, X and Y, are same, whereas Z can be different. So if we have Z, the value of Z to be different, then this at the next iteration, this information is propagated in the this particular cell, that is the Y position. So it is just like a left directional information flow. Similarly, we can take the right directional information flow by observing the equivalent RMT set. Here I term this EQI and SIVLI as SIVLI is the RMTI and its sibling RMTs, and EQI is the RMTI and its equivalent RMTs. Now our selection criteria is we want maximum information flow on any one direction. So the strategy is we can pick up the nonlinear rules in which either all RMTs of SIVLI or EQI have the different next state values. That means what? If we consider all such set equi I, then if for every one of these sets, these values are different, that means whenever there is a change in these sets, it will be always propagating towards this. So there is a maximum flow of information in this direction. Similarly, if we consider that in the rules, all the sibling sets have different nested values for each of these sibling RMTs inside this residual I, then we ensure that there is a flow of information towards right direction. Now this is our strategy. So this strategy is actually equivalent to the property of right or left permittivity, which is a very well-known term in the study of chaos. And you can see that here in my strategy, I have taken either or, that is or is exclusive or. So we reject those CA rules which have maximum information flow in both directions. Because if we just look at those CAs which have maximum information flow in both directions, it kind of creates some symmetry in the CA, resulting in triangular patterns and fractals. For example, if you look at rule 90, then rule 90 has the behavior where it has flow of information, maximum flow of information from the both directions, and it is creating such kind of figure where it is clearly you can see the fractals, Sierpinski triangles, and which is not useful as random number generator. So we reject those CAs. We also have some other rejection criteria. Our requirement is long cycle length. So how we can ensure that the cycle length is going to be very long? First criteria we want to check is there is no inclination of the configurations towards converging to any fixed point attractor. And we want fewer number of fixed point attractor, because we know that there will be some cycles. We can't get only one single length cycle and all the other configurations part of the same cycle. That is not feasible in periodic boundary CA. We want only small cycles, that is the fixed point attractors, single length cycles rather, which is having only trivial configurations like all zero, like 0 to the power n, 1 to the power n, and so on. These are the trivial configurations which we want to be separate from the non-trivial configurations, and the non-trivial configurations are forming some cycles. That is our target. So we want trivial configuration to be separated from the non-trivial configurations, and non-trivial configurations do not form any fixed point attractor. For this, we check if there is no non-trivial fixed point attractors for any cell length in the CA, and whether all the non-trivial configurations are non-reachable from any trivial configuration. For checking this too, we use the Diffusion graph. This Diffusion graph is basically representation of any overlapping sequence. For us, we know the RMTs, that is 0, 0, 0, 0, 0, 1, 0, 1, 0, and these are this can be thought of overlapping sequence. So we can represent easily any CA by Diffusion graph. In Diffusion graph, the edges are x, y, y, z, where x and z is taken from the state set, and y can be s to the power k minus 1, where for 3 neighborhood condition, we have to take k as 2. So here, for 3 states C, I have shown it. You can see this 1, 0, 2, 0, 2, 0. These edges are the RMTs basically. So if we take any cycle here, it will be a sequence of RMTs, which is nothing but a configuration. And the next configuration will be represented by the corresponding nested values for each of those RMTs. So by observing the Diffusion graph, we can get idea of the cycles, as well as the cycles means the configuration corresponding to the cycle, as well as the next configuration corresponding to the cycle. So here, if we just consider the divergent graph to be modified, having only the edges with self-replicating RMTs, that means the RMT has nested value as same, like the middle or the self position, then obviously that any cycle in that graph is going to represent a fixed point attractor. In this way, we can detect if there is any fixed point attractor in the CA. Also, we want trivial configurations to be disjoint from the non-trivial configuration. Now, if we want to check for any particular trivial configuration, say 0 to the power n, for that again we can modify the divergent graph. We'll take only those edges for which the nested value is 0. So, for example, if we take here, it is if we take just 0 edges, then in that graph, does any cycle will represent a configuration, and if that configuration is a non-trivial configuration, then corresponding to that cycle, actually we are getting a trivial configuration as the next configuration. So that means from a non-trivial configuration, we can reach to a trivial configuration. So cycle representation in that graph, we are discouraging. And if we get such CA, well, those CAs we are rejecting. So these are the rejection criteria. So after doing this, we can get a lot of CAs. But same problem still is there, that how we can find such CAs, how to represent such CAs, or how we can look for such CAs. For that, we introduce the rule of first degree. If we take the rule R of XYZ in this form, where this C0, C1, C2, all these are some constants, and we take all possible combinations between the X, Y, and Z, and the degree of this equation is 1, then this CA we declare as the rule of first degree, or simply first degree CA. For our case, we are considering D as 10, but we can take D as any value. And also accordingly, if we have more than 3 neighbors, then we can change this equation and we can get similar first degree equations. So for fixing one particular rule, we have to fix only the constants, because if we stick to this rule, only the constants will be denoting the, if we give the constant values, by using those constants, we can directly get the rule. Here we can see some examples of rules of first degree from elementary CA, that is tree neighborhood two-state CA. These are only some examples. Here, if you observe, all these CAs are obviously not satisfying our randomness criteria. For example, if we take C0, C1, C2, C3, and C7 as 0, then the rule becomes a linear rule. See this? These are linear rules, and we don't want linear rules. Similarly, we can find some other criteria also for which the rules are not going to satisfy our criteria. Now, if we observe this equation for XYZ, to like if the CA is going to depend on all neighbors, XYZ has this term is only here, present only here. So C0, if C0 is greater than 0, it can be dependent on every neighbor, but you will see that C0 can't be more greater than 0. So we can directly omit this. Now C1, C2, C3, this makes the CA dependent on the pair of neighbors, and C4, C5, C6. This make the CA dependent on the cell left cell and right neighbors. So these are the way we can we can design our constant to make the CA appropriate for our requirement. Now, just like I was telling, here you observe C0 is always 0. We can't get any rule where C0 is more than 0. So we omit that part, and the equation is changed now to have from here C1xy plus C2xz and so on. So any first degree CA we can represent by this constant C1 to C7. These are called the parameters of the first degree CA. We have run our equation by changing all the parameters, and we have got this many number of rules which have maximum information flow in at least one side. Now among them, some rules will be there which have information flow in both directions, and some will be linear. These are the rules which are not satisfying our criteria, so we remove those rules. Here I am showing some examples which some rules which are satisfying our criteria. You can see we have sometimes left directional information flow, sometimes right directional information flow. The rule itself can be represented by a simple equation, but more than that, we can simply represent it by a 6-tuple, these numbers, or maybe we can take the string and we can say that this is going to be our number. Now we want to see how far these simple rules can go in terms of the randomness quality. Here we use the window-based scheme where a window of length W is taken and the numbers are extracted from the window. Here the both W and the N, that is the cell length, are variable, and to make the window cover all possible combinations of the number, N needs to be actually very large. We take here any arbitrary non-zero seed for window, and other cells we initialize with 0 to the power n minus w minus k, w minus 1 and k, where k is any state. We can take simply 1 also. And for any seed, we generate the numbers from n plus 1th configuration onwards, because as we have taken the remaining states as all 0, 1, we expect that some time will be required to fill up the or the compensate the zeros there in the initial configuration, and so we give that time. For our implementation, we have taken window size of 12, where last 32 bits of the binary string is taken as the generator number, and n equals to 51. This is the result. Here you can see that this was the previous result of machine twister and its variant, and this is our CA. If you look, these are exactly comparable to the previous result, but here we have considered the smaller version of the test matrix, die-hard, which contains only 15 tests, NIST, that is the 15 test package, and test user on rabbit file 25 tests. These are the smallest packages, and it doesn't require large file size. So for that only we have taken this version of the metric. And if we see the space-time diagrams for some random seeds, this is the rule and this is the parameter. And if we see, we can see that there are no patterns in the generated space-time generator numbers, which can be represented by the space-time diagram. So finally, we conclude that we have identified a simplified form of representing any CA, not only decimal CA, but obviously that cannot like all the CAs cannot be represented by this form. Only a small set of CAs can be represented by this form. we have shown that even these simple CAs, if we consider decimal CAs, they are good as PRNGs. And this scheme will work for any distant neighborhood CA by properly choosing the parameters. But the future work remains that how they will behave in terms of the other global properties of the CA, like reversibility, like number conservation and all. That is still not done. And whether increasing the degree of the CA will play any role in improving randomness quality, that is not explored. This is only first degree equation. We can change the degree of equation. This is a whole new domain, like we can just manipulate the equation according to our wish and we might get different kind of CAs. And there will be characterization of such CAs in more details, which needs our consideration. And finally, I want to say that these decimal CAs are really very interesting. It has very very bright future in the randomness domain, but more characterization is required. And also in terms of the other global properties also, decimal CAs are not yet explored. So that is only part of the future. Thank you. These are my references.
Thank you, Kamalika, for your presentation on your interesting work. This is very interesting. So we are expecting questions from the audiences. So audiences, you are requested to ask the questions. Any question?
Kamalika, I have a question.
Yes, sir.
Kamalika, you were saying that
Yes, sir.
In the future scope, you want to make it, you want to work with M neighborhoods here. Okay, you want to extend the neighbor for arbitrary M. So do you think if you increase instead of 3, say 4 or 5, ultimately randomness quality will be increased?
No. Because this Smith's work is already there, which shows that if we increase D instead of M, and if we keep D fixed and increase M, both will be directing us to the same thing. So I don't see hope in that domain.
So you are saying that you want to explore it for D state as well as M neighbor. So it may be like,
I'm just saying that not in terms of randomness quality, but if we want to explore some other properties, which like if we increase D and M, the same problem of representing the rule will be there. That problem we might address by using this simplified form. That I wanted to mention. So those CAs might be interesting to see, but in terms of randomness quality, I don't know. I don't see much hope in that. If we consider two-state and we increase the number of neighbors, then Smith's work says that they are going to be like we can get an equivalent CA, but whether it will be beneficial, no idea.
Any more question?
Ma'am, I have a question. That
Yes.
In the evolution, if there is any noises come during the information flow, can I add in at that point that based on the degree of endurance or the tolerance of particular CA, we selecting some rules. I mean, it is the more filtering of that PRNG. Is it possible?
Can you please repeat again?
During the evolution, if any noise come, then a perturbation occurs. Is it possible to more filtering that type of CA which can tolerate that type of perturbation?
Okay. So you are saying instead of the CA itself to be chaotic, if we add some kind of extra noise inside it, then can the CA absorb the perturbation? Yes, they might be, but I don't know which CA will be able to absorb it, but such kind of CA will obviously be there.
And in the rejection criteria, can I add that point that based on that degree of endurance,
Okay.
select that type of CA?
Okay. But yeah, that you can do. But in case of this synchronous CA, we this synchronous and not stochastic CA, we give that perturbation information inside the initial configuration itself. No, so if you want the CA to be absorbing that perturbation information, then it is going to come to a stable state after some time, and that CA will not be useful for being a PRNG. Maybe that will be useful for some other applications, or they might give us some useful behavior, but that CA will not be useful for a PRNG, so that we can't include as a rejection criteria for PRNG.
Okay, Kamalika, I have a question. The CAs you have used, is it reversible or just a general reversible?
I have not checked reversibility here.
Okay.
So some may be reversible, some may not be reversible.
Okay.
For example, here you can see rule 45 is there, which is reversible for odd n. Rule 90 is there. Rule 165 is there. Rule 240 is there. Rule 85 is there, which are semi-reversible or reversible for some n or for all n. But similarly, some other rules are also there. 135 is there. 195 is there. These are not reversible rules. So it is a combination of them.
Do you think non-uniform CA will give better result?
Non-uniform CA, in terms of better result means in terms of randomness quality, you are saying. Non-uniform CA, for non-uniform CA, we have this option of representing the rule, or if we consider only two-state three-neighborhood condition, that is non-uniform ECA, then that non-uniform ECA space is huge. So the shortage of rule will not be there, and this what should I say? This representation issue will also not be there. But as per the records, we have seen simply using non-uniform CA, it is not getting better result. These are the existing results, and it is not good enough. So simple non-uniform CA are not going to give us good result. We have to manipulate it, just like we have done in the previous paper. So that here we are not doing any kind of manipulation. We are just extracting the configuration as it is. That thing, just in the raw form, we are using the CA configuration. So here it is the intrinsic property of randomness that is reflected. But that in that case, for two-state CA, we are not getting two-state non-uniform CA, we are not getting that benefit.
Thank you, Kamalika, for your nice presentation.